Last lecture we talked about the response of a material to stresses and strains. In this lecture we're going to actually move up a little bit from that view and look at the device responses, and we're going to focus on the most fundamental device in MEMS, which is a beam. We at microscales do not have gears or linkages or hinges of different types. The reason for that is that, first of all, any form of structures that are moving past each other and they're in touch with each other, you are dealing with significant amounts of wear and tear and friction. In many cases it's so much that you cannot actually do the moving part of the device, and for that reason we just try to avoid it altogether. On the other hand, when you have these hinges or these gears or linkages that you have at macro scales, if you look at the required precision that you have in order to make these, it's amazing. You cannot get the same level of precision at small scales. So if you look at the ball bearing, for example, the gap between different structures is sub-millimeter, much smaller than a millimeter, but the dimensions of the device itself is centimeters or much larger than that, right? So you're talking about a significant level of difference between the, let's say, the gaps between these structures and the actual dimension of the structure. So a little bit of movement here doesn't matter that much. The precision you have is much better than what you can get at microscales, where you have a device that is on the order of a few microns, and then the precision, the gap between the structures, is on the order of a few microns as well, right? So for example, if you make a gear set at microscales that can actually go and interlock to each other and move, well, the space between the teeth of this gear has to be etched, so it cannot be below your lithography resolution, and you get that much backlash, okay? So in most situations we don't actually even have gears. Everything that is connected to something else at microscales is usually done, is connected through a beam, a straight beam that is fixed at one end and connected to a device at the other end, or maybe both ends are moving relative to each other. But remember, we're making everything out of, basically we're carving this structure, right? So we're not connecting different pieces to each other, we're carving a structure out of a film or a substrate. So what happens is that the beam becomes your most important mechanical element. Now, life is a little bit easier because your beams are usually, for MEMS devices, have a rectangular cross-section as well. Rectangular because it's from a thin film that you etch using DRI, for example. So you get vertical sidewalls on the sides and vertical sidewalls at top and bottom surfaces, a rectangular cross-section. It makes a lot of your calculations easier. And we need beams for almost everything in MEMS. You need them for, or we need to study the beams or beam responses in every case, for a lot of cases. So a beam is used as a spring in MEMS applications. So you want to know the deflections of them and their response to forces. They are used to apply stresses and strains and basically connections between different parts of a system. You need to figure out what are the stress-strain relationships inside these beams. Beams are used as springs, or they could be the only moving part in your structure, but nonetheless they will affect the dynamic behavior of your structure. So again, you need to figure out how a beam responds or behaves. Again, good news is that you've seen beams before, actually in more general situations. Now we focus on what is relevant to MEMS devices. Examples of beams applications in MEMS. Well, the first device on the left is an AFM probe. You have a sharp tip that you move onto a surface, and then the tip goes on up and down, follows the topography on the surface. And when you look at this from the mechanical point of view, you have a cantilever and displacements at the tip of that cantilever. What you need to do later on is to figure out how much this is displacing in response to those forces at the surface. But at the end of the story, your device, your measurement tool, is just a simple beam, a cantilever. One end fixed to whatever is moving it, the other end following the topography on the surface. The beam can be your device. So in this case, what we have is a clamped beam. Both ends are connected to the substrate. This middle part is a beam that is vibrating in plane. This is a resonating structure, resonant beam, and I'm using it for its dynamic behavior. Another example of a beam that is the device is this. You can see that I have this free beam over here that is actually my device. I'm applying an electrostatic force to the ends of this beam, making it longer or shorter. But at the same time, you can notice that I'm using beams over here as well and over here as well. This is a connecting beam. This is a, let's say, a structure to minimize the anchor loss. This is a beam to keep this device in its place. So every piece of this device is a beam. The device itself is also a beam. You can see here two uses of beams. In one case, I have these straight beams, cantilevers. One end is connected to the substrate, the other end is free. Two of these beams side by side, if I move them closer or farther from each other, relative displacement between them, I can measure change in capacitance between them. So that's one application of the beams. But the one that is more relevant is this beam that you can see is folded over here in a similar structure over here. So what this beam here does is that it provides a mechanical restoring force in that direction, right? And the beam here does it for this direction. This is actually a corner of a two-axis accelerometer, x, y directions, and those beams are acting as the springs for keeping the proof mass, which is this bigger part here, in its rest position. A beam can also be used as a torsional spring. So at the corner of this mirror, you have two beams that basically tilt it back to the original position once you don't really need to rotate it from the rest position. And then, as we said, you can use beams as parts of a major design, bigger design, just to connect it in place, hold it in place. Okay? So let's study beams. Here is a basic structure. I have a simple beam, uniform cross-section for the entire length of it. And let's assume I apply a force F to the two ends of this structure. So one end could be fixed, and the F that I have at one end could be the reaction from the support. But let's assume that I'm applying a force F to both ends of this beam so that it's not moving, but it will respond to that force. If the length of the beam is L and the width and height of it are W and H, I can show that the internal force in response, the internal stress in response to that external force is going to be this much. So the force is divided by the area of the beam WH. And if this is made of some isotropic material, or I'm using it at a given direction in my crystal surface, that I can basically simplify the whole thing to just one E number, I can show that the amount of deflection I get, the displacement, not deflection, the displacement that I get is given by this expression here. So epsilon, the strain, is given by stress over E, and I know E from here, so I can figure out what the strain is. Now, if I want, so remember epsilon is the normalized displacement, so it's delta L over L. So if I start with a length of L, a stress sigma is going to make it, let's say tensile stress, make it longer by delta L. And I can go and show that amount of delta L is proportional to the original length through the expression shown here. And this is basically Hooke's law. So I can show that, if I assume this beam is a spring and I'm applying a force to it, how much does this spring elongate? Well, that much, right? Delta L. What is the effective spring constant? Well, it's shown here. It's proportional to EWH over L. This is called the axial spring constant of my beam. Okay? So how do these numbers look like? So let's assume that I have a beam which is 100 micrometers long and 10 microns wide and 10 microns thick. And the Young's modulus is 170 gigapascals. The first question is, the question is that what is the axial spring constant for this beam, right? And so I know that K, oops. EWH over L, or E times the area over L. And I have all the numbers that I need, plug them in, and you can show that K axial for this beam and these dimensions is about 170 kilonewtons per meter. So we calculated it, but what does it mean? Is it a large number? Is it a small number? Well, consider the forces that you have at this scale. So let's say a typical value for a force is about a micronewton in most cases. A millinewton is a huge force, right? So what you can do is that you can go and see how much this beam elongates if you apply 1 millinewton to it. And then if you do the math, it's about 6 nanometers, right? So a huge force of 1 millinewton when applied to this beam just makes it longer by 6 nanometers. A more reasonable force value like a 1 micronewton is going to make it longer by only 6 picometers. The conclusion here is that you really cannot use these beams as axial springs that easily. They are very, very stiff, right? So even if I make this beam, let's say only 2 microns wide, and the height is usually not under my control because that's the thickness of a film that the process engineer specifies and will not change it for me. My only improvement is about a factor of 5. I make it 5 times less stiff. It is still a very, very stiff structure. So what to do? Well, the solution is easy. So instead of using do is that I can look at their bending behavior. So instead of applying the force parallel to the beam, I apply it normal to the beam. And then the idea is that I get more deflection, more displacement from the neutral position by doing so. So bending of a beam is a problem that has been studied before in your courses. We're going to keep it very simple. Just some reminder about the terminology. If you have a beam and we're looking at the section of that beam, that is bending downwards as shown here. So it is assumed that this was straight at the beginning. Now we are bending it downwards. The top side of the beam will be stretching. The bottom side of it is compressed. So if I look at the stress developed inside this beam, at the top of this beam, remember we use a positive sign for tensile stress. I have positive stress, and at the close to the bottom surface of the beam, we will have negative stress, compressive stress. So it's a continuous piece of material. You're going from positive stress to negative stress. At some point, you go through zero stress, right? So the axis that goes through the beam and this zero stress region is called the neutral axis. It's an imaginary border between where you have tensile stress at the top part of the beam and compressive stress at the bottom part of the beam. Because the stress along the neutral axis is zero, it will not elongate or become shorter. Basically, the strain will also be zero along the neutral axis. Now, once you have that, you can show that through some basic geometry, it's very simple in terms of geometry, you can show that at distance y from neutral axis, once you have some bending, the amount of strain, basically the change in length, so if you take a small piece and bend the beam downwards, the change in length of that small piece that is located at distance y from the neutral axis is proportional to that distance and inversely proportional to the radius of curvature that you have here. So epsilon at distance y is proportional to y over rho. And we can go through the derivation during the live sessions if there is interest, but this is something that you've seen before. I'm going to get to the conclusions in here. If there are questions, if you need a refresher, let me know during the live sessions and we'll go through the details. But anyway, so it's y over rho, and then we know that the radius of curvature for a structure is found from the second derivative. It's 1 over the second derivative of the deflection equation, right? So if psi of x is, let me maybe draw it here. Let's say this is the original location of the neutral axis, and the beam has deflected because of some external load to this. Psi of x is this distance as a function of x. So this is your x-axis, right? So our x-axis is this direction. Okay? So psi of x is specifying the deflection, how much that beam has moved from its neutral axis, from its original location. And what we can show, or what mathematically you can show in your calculus, I think you've seen it, is that the deflection equation gives you the radius of curvature. So the radius of curvature at any location is 1 over the second derivative of psi of x at that location, so rho of x. Okay? So once you know that, you can location from that expression. So a strain at distance y from neutral axis is y divided by the radius of curvature, but then you can show it is times the second derivative of the deflection equation with respect to x. Now, what this tells you is that this strain at a given location, at a given x, the closer you are to the surface, the higher is the strain. So if you go to the top surface, it's going to be the largest positive strain. If you go to the bottom surface, it's going to be the largest negative strain. What that means is that if you want to measure strain in this structure, these are the optimum places for your strain gauges, right? So in macro scales, if you look it up, this is where you put your strain gauge. You attach it to the close to the base, well, it is on the top surface or bottom surface of the structure, not only because you don't have access to inside the structure, but just another main reason is that these are the best surfaces in terms of the signal strength that you get. Now, you can go and find the stress at any distance y from neutral axis. You know, it's a linear material, isotropic. So stress at any y is just E times the strain, and I already know the strain. So this is the stress at any distance y from the neutral axis. And then the next thing you can do is that you can go and look at the moment of inertia that is applied here. So if you calculate the moment x, so what you do is that you multiply the stress by a very small area times the distance from the neutral axis to calculate the moment produced by that component of stress, integrated from the bottom surface to the top surface to calculate the total moment of inertia. And what you can show at the end is this equation, which is known as Euler-Bernoulli equation for beam bending. So what this tells you is that the moment of inertia for a beam of a rectangular cross-section, this I is just proportional to the dimensions of the beam. We'll see that in a second. E is Young's modulus. Psi of x is your deflection equation, and m of x is the moment of that is applied to your structure. Okay? So this we have seen before. So we have a differential equation that once you know the moment applied to the beam, can give you the deflection. We solve this deflection equation, And psi of x is what we want to find out. We want to know how much the beam is deflecting, how much the beam is moving from its rest position due to the load. Now, it's a differential equation. To solve it, you need boundary conditions. And these are your typical boundary conditions in MEMS. Actually, your typical boundary conditions in MEMS are just these two. Right? You either have a free end, it's a beam whose end is free, and in this case, well, you don't have control over this log psi of x, but you can show that the second derivative of the psi of x is 0, right? Basically, you don't have any moment at the very tip of this beam, and the third derivative is also 0. So that's a boundary condition you can apply to this end. A fixed end, you can see that, well, there's no movement here, so psi of x is 0. And for a clamped end or a fixed end, what we will see is that the slope also doesn't change. So if it is bending, and so it is bending like a hinge right now for my arm, but if you look at the ruler and you apply a force to that end, there is no change in slope here. So the derivative of psi of x at this location is also 0. A third condition here shown as a pinned boundary condition is what I have right now. So psi of x is 0, but the slope can change here. It's like I have a hinge here, right? In microscales, as we said, this doesn't happen very often. You don't really get a hinge. It's always a continuous connection between the beam and the substrate. But just in case that in a situation this may simplify your calculations. For example, if the dimensions of your beam are much, much larger than, let's say, typical anchor points, you may assume this is a pinned connection. There will be some, let's say, error in your calculations, but in most cases, a pinned boundary condition makes your calculations much, much easier later on. And then what you have here is that the second derivative of the psi for a pinned connection is also 0. So you have a second order differential equation if you have a moment for your input, for the input applied to your beam, and you need two boundary conditions. You look at your beam geometry and you pick the right boundary conditions from here. Another situation that happens in MEMS is a guided boundary condition. This is where, again, you have a big plate and the beam has connected to it. The plate goes up while you don't have a hinge, and it's not a fixed condition. The end is going up and down. But it is very similar to a clamped end. It's the derivative of the psi doesn't change at this end either, but psi can be non-zero. And this is a problem that you will see in your assignment, and you solve it, and then you estimate how the beam behaves in that kind of a situation. Now, the question here, and I'm almost sure that you've seen this before, just an example, it says find the deflection equation for a cantilever with a point load applied to its end. So, in this case, we have applied the force F to the tip of it, cantilever beam. The base is clamped, the tip is free, and we want to solve this equation to see how the beam deflects in response to that force. So the equation that I need to solve is this. So I know EI times the second derivative of psi is equal to the moment. At any location x, I can show that, well, the moment is that force that I have at the tip times L minus X, right? So this is the distance here is L minus X. So that's the moment applied to this beam. So I have psi of X at any location X from this expression. So let me just maybe simplify it. So the second derivative of psi of X with respect to X is just minus F over EI over times L minus X. Now, what is I? I is the second moment of inertia. We can go and show that for a beam of, let's say, width W and height H, I is given by this expression, WH cubed over 12. And this is a beam that is deflecting downwards, right? So for the same beam, if it is deflecting in this direction, I will be HW cubed over 12. The way to remember this is that think about which direction gives you the most resistance. So if I'm bending the beam downwards, if I put two of these two beams side by side, I expect the moment of inertia. I expect twice the amount of resistance, right? So I expect the width to be linearly proportional, or the moment of inertia to be linearly proportional to that width. On the other hand, if I make this twice as thick, it is going to be much, much more stiff, right? It's not like twice as stiff, it's significantly more stiff. And you know, just do it with two rulers on top of each other or side by side, if it is not convincing enough, if you have a hard time imagining it. If you put two plastic rulers side by side, same dimensions, they become twice as resistant to bending. If you hold them together very, very well, ideally it should be glued, and on top of each other, they actually become 8 times, it becomes 8 times harder to move them downwards. So I, the moment of inertia for this situation is this. So let's just call this IZ and then IY. So this is deflection in Z direction, that's in Y direction, for example, right? So just keep that in mind. So it's WH cubed over 12 with H being the thickness in the direction that you're applying the force. Now I can solve this equation. I can integrate once and see that the first derivative is just going to be minus F over EI times Lx minus x squared over 2 plus some constant 1, and then integrate this one more time, and I have minus F over EI times Lx squared over 2 minus x cubed over 6 plus C1x plus some C2, right? And then C1 and C2 I have to find from boundary conditions. I look at the fixed end, those are the easier boundary conditions to apply, because at the fixed end at x equals 0 for that beam, I have psi of x equals psi of x equals 0, and then the first derivative, so psi prime of x, is also 0, right? So this is easier to apply. And then if I apply that right away, I will notice that C1 is 0 and C2 is also 0, giving this deflection equation for me. So psi of x at the end of the story, it's just going to be minus F over EI times Lx squared over 2 minus x cubed over 6. And you can simplify this more and make it look nicer. But anyway, that's the answer. Notice that I, we didn't really have to calculate, but for a beam of rectangular cross-section, you go and use, for example, this I if it is bending downwards, or the other one if it is bending in plane. Okay? What I can find out now is that I can show that for this force F at x equal L, I want to calculate how much deflection do I get. So this is the original displacement. This psi at x equal L is going to be minus F over EI times L cubed over 2 minus L cubed over 6. Okay, so it's going to be minus F L cubed divided by 3EI. Okay, and if I want, I can specify an effective spring constant. So effective spring constant is going to be F over psi of L. You know, when I apply force F here, it displaces from its rest position. How much does it displace? I normalize that displacement with force, and the effective spring constant is just going to be 3EI over L cubed. And the negative sign goes away. It's a positive spring, right? So it's trying to restore the force, go back to the original position. So 3EI over L cubed is the effective spring constant for this beam. We notice that it is proportional to length cubed. If I want to make it softer, I can easily increase the length. I also comes into play, WH cubed. So again, you know, make it twice as wide, it becomes twice as stiff. Make it twice as thick, it becomes 8 times more stiff, right? So all those things you can see here. It's proportional to E, so that's expected. And one other point that I can make here, or I can see here, is that the effective spring constant depended on the boundary conditions, right? So if I had a different set of boundary conditions, I would get a different deflection equation and therefore a different effective spring constant. And we'll see that in a couple of slides, that, you know, how different boundary conditions affect your effective spring constant that you have. Now, the challenge is that, well, we calculated this using the moment that we had, but in this case calculating the moment was relatively easy because we had a force applied to the end of the beam and we just calculated the moment from there. But sometimes you have a combination of forces, right? So you may have a distributed force applied to the beam, in this case shown as Q. Distributed force. I'm not sure what happened here. So you may have a distributed force Q along the length of your beam. You may have moments applied to it. And you also may have shear forces applied along the length of this beam in different ways. Now the question is that, you know, how do we consider, or how do we calculate the bending of a beam under all these conditions? Or if only one of them is applied, how do we just go and do the calculation for the bending without going through all these conversions to moments? We first notice that this beam is under static equilibrium. So what you can see is that the sum of the forces should be 0. So Q times dx, what is pushing it down over this length dx, plus the differences in shear forces should be 0. Immediately you will see that gives you one relationship between the shear forces and Q. You also notice that the moments should add up to 0 because this thing is not rotating either, right? So it is a static problem equilibrium. So the moments that you have applied to this small piece of beam should add up to 0 as well. So you have one moment from m plus dm. You have a pair of moments from the shear force applied to this end. If you take this one as the origin, then V doesn't apply a moment here. And then the distributed force here will also create a moment, and you can integrate it over the length from 0 to x and figure out the moment due to the distributed load. At the end of the story, all those moments should add up to 0 as well. And neglecting higher order terms, from the first equation you can show that the change in shear force across the length of the beam is proportional to the load, to the distributed load, and the change in moment across the length of the beam is proportional to the shear force. How do we use this information? Well, if that's your beam and psi of x is the deflection, what we can show is that this is the original Euler-Bernoulli equation, but we already know that m is the derivative of m will give you the shear forces. So you can use this differential equation. It's a third order differential equation if you have shear forces and not moments. We could have actually done this for the problem that we just solved, right? So we had a shear force at the end of the beam. You could have solved it with this equation instead of calculating the moments and solving it here. If you have a distributed load, you can go and maybe use the fact that the shear forces are proportional to your distributed loads through this expression, and you can solve this equation directly, right? So if you are given a distributed load over the length of a cantilever, just solve that last equation instead of going back to calculating moments and then solving it. At the end of the story, what happens is that for typical loading conditions where, for example, Q is a constant over the length of the beam, in most cases at MEMS at least, you get very simple solutions here. So Q is a constant. There is no dependence on X on the right side of the equation. If you want to solve this equation, all you need to do, for example, I'm talking about this one here, is to integrate it 4 times. If you're solving this equation and there is no change in V, let's say only applied to the end of the beam, all you need to do is to solve it by integrating this equation 3 times. Looking at this most general case, at the end of the story, you get a solution like this. You integrate that equation 4 times, you get a general solution that is a polynomial of order 4 plus 4 constants that you have to figure out through applying the right boundary conditions to your structure. Okay? And that's basically it. So if you have a distributed load, you get this. If you have a shear force, you get a third order polynomial. If you have a moment, you get, independent of x, you get a second order polynomial. We saw for our case the moment was dependent on x, so we get the third order polynomial. But in the most general situation, the order of the polynomial is 4. Okay. So here is a problem that we can solve using what we just learned. The question is, how much does a cantilever bend under its own weight? So you have made this cantilever of length L and let's say width and heights W and H, and you want to know how much it bends under its own weight. And we look at 2 different cases. So let's go back to so I have a cantilever here. Obviously, when I lift it, it's going to bend down. It has some weight, and the weight is distributed along the length of this cantilever. So if you look at it, if you check this piece dx, the weight, the force applied here, gravity is acting as a distributed force along the length of this cantilever, right? And you can find that force. So Q, you can say the total mass is m, the force is mg, and I normalize it to the length of this device. So my force, my distributed load is mg over L for this device. If you want to specify it in terms of the density of the material, so it's going to be the rho, the density of the material, times WHL, that's the volume, divided by L times G. or rho WHG. Okay? So this is the distributed load on this cantilever. Now I want to find how much will it deflect under this load, right? So basically, what is this psi of x? I'm going to change the color here. So if this deflection from this neutral position, psi of x, I want to find out psi of x, and specifically I'm interested in psi of L, the deflection at the tip of this beam in response to gravity. So the equation that I go and solve is this, so EI, the fourth derivative of psi of x with respect to x is Q. Okay? And I sometimes may not show the negative sign that basically indicates the direction of the deflections. It's minus Q. But we know that, for a regular beam, positive Young's modulus and everything else, once you apply a force, the deflections are in the same direction as the force. So as long as you check that at the end and make sure they correspond to each other, as long as you do not apply a force and the beam goes up, you should be fine. But anyway, if I solve this equation, I have this for psi of x as we showed on the previous screen. So it's going to be Q over EI x to the power of 4 divided by 24 plus I'm running out of space here. Plus, let's say C1 x cubed plus C2 x squared plus C3x plus C4. And actually, if you add these coefficients one by one, so you will have C1 divided by 6 times x cubed, and then C2 divided by 2x squared, and then C3 and C4. I just absorb that 6 and 4 into the coefficients themselves. Okay? Now, for a cantilever, I know that the boundary conditions psi of 0 is 0 and psi prime of 0 is 0. So therefore, this gives me immediately that C3 is 0 and C4 is 0. This is for the fixed end. For the free end, the psi of L, I know that psi double prime of L is 0 and psi triple prime of L is also 0. Right? The second and third derivatives over there are 0. And this gives me the values for C1 and C2. So I have the final answer here at the end of this story. Psi of x will be given by this expression. So minus Q over 24 EI x to the 4 minus Q over 6 EI L times x cubed minus plus QL squared over 4 EI x squared. Okay? So that's the equation for psi of x at the end of the story. Actually, I have the simplified version, so this is going to be, I missed that, 1 over 24 x squared q times over EI. So it is an EI over EI. Okay? And now you can go and figure out what is the deflection at psi of L. So just plug L in here. Psi of L is so QXL squared over 24 EI times L squared minus 4L squared plus 6L squared. So that's 3L squared here as well, right? So it's going to be Q over 8 EI times L to the 4. Something is, 3. 3, okay? So that's the amount of deflection under its own weight, the beam under its own weight. Now let's look at two cases. Case 1, we have a length of 1 meter, thickness of 1 centimeter, and width of 5 centimeters. Same material as before. Let's say E is 170 gigapascals and rho is 2,000 kilograms per meter cubed. So this is silicon. And for a G of 10 meters per square second, what you get is that displacement at the tip of that beam is going to be about 2 millimeters. Or this is about 0.2% of the length of the beam. 0.2 millimeters is how much a 1 meter beam will deflect. This is measurable, and this is a fairly thick beam, right? 1 centimeter. So if it was a bit narrower, thinner, it would have been much more easily to see that. But let's just go and see what scaling does to this issue. Let's scale all dimensions by a factor of 10,000. So I go from an L of 1 meter to an L of 100 micrometer, a thickness of 1 micrometer, and a width of 5 micrometer. This is the very typical beam for MEMS devices. And if you go and do the calculation for this beam, now you see that psi of L in this case is only 0.02 nanometers. Or if you normalize it by length, it's 0.2 ppm, parts per million of L. That's a very difficult amount of deflection to measure. Even when you normalize it to the length of the device, which is a small length compared to the original beam, it is still a tiny fraction of that length, right? So when you shrink it, let's say lesson here is that inertia is not going to affect, or gravity is not going to affect the behavior of this beam that much. It's not really deflecting from its rest position that much because of its weight. And this is true in most MEMS devices. In most situations, if you're looking at the static response of these devices, you can ignore the effect of gravity on the initial displacement of these devices. Now, for static bending of the beams, we have this table for different on the boundary condition that applies. So clamp free is the cantilever that we've discussed so far, and you've seen that solution already. But clamp free with a distributed load will give you a different deflection equation. It will be less, right? So if you distribute the same amount of force on that beam, you expect a smaller amount of deflection, just because the force that is close to the base is going to affect this beam less than a force that is applied close to the tip of it. For a clamp beam, the beam that has both of its ends fixed to a substrate, you get a stiffer response, a stiffer structure. And then, as I said, we have another situation where you have a guided boundary condition. So you can have a beam that is guided, right? At one end, let's say the proof mass of a accelerometer is moving here. The other end is your substrate. A beam that connects the two to each other will have a clamped guided boundary condition. And as I mentioned, you will see this in your assignment. Now, boundary conditions that we are applying here are really simplistic. They are only considering the simplest situations, ideal situations. For MEMS fabrication, you can have situations where the material is not really going to maintain its uniform cross-section for you because of, for example, the undercut you may have at the interface between different materials. Another issue is that, once you release the structure, you will have a little bit of undercut underneath the edges of your features, your masks. And if this beam is bending in and out of plane, well, it's going to bend a little bit of this anchor point in itself as well. So this is not a fixed boundary as you assumed anymore. It is bending with your beam. And these are examples of those situations. Here is another situation that can complicate the, simple calculations. The vertical sine wall that you assumed you were going to get, may not be vertical. You may have some angle to it. So instead of a rectangular cross-section, you may get a trapezoidal one. That's not a big deal, really. So that's actually between the two figures, you see the effect of RIE versus DRIE. In this case, we have gone almost straight down if you use a DRIE system. In here, RIE. It looks like vertical. It's still pretty steep, but a slope can be measured there. Now, as we mentioned, we already have talked about the stress in thin films. With beams, the stress in a film is going to complicate the matter. So what happens is that, let's assume in this situation, we have a beam that, let's say, is made of a metal layer. We have deposited this metal layer, let's say, through evaporation. And this is an existing feature on the wafer. As we are evaporating more and more material here, or it could be CVD or even sputtering, what happens is that the region closest to the surface will be at the temperature of the substrate. As you move away from that substrate, you will become, let's say, if the process is hot, you will have a slightly hotter and hotter regions in your beam. And therefore, once you're done with the fabrication, the temperature gradient that you have here, as you cool down the structure, will cause you have a different level of stress throughout that film. So in this case, we are assuming that the thermal expansion coefficient of this beam is larger than that of the substrate. Once you cool it down to room temperature, you will have not only a compressive stress inside this structure, but also a stress gradient. Right? So you will have more stress at the bottom compared to the top of that structure. And this stress gradient is going to cause the problem. The actual value of stress, the compressive stress, you can design around it and make sure that you accommodate it. But when you release this, when you get rid of this sacrificial layer at the end of the process, well, the assumption here is that the first thing that happens is that the compressive stress will release itself. Well, because you have a free end, that's not a problem. It just stretches a bit, and then the free end will be a little bit farther than where it was before release. That's not a big deal. However, that stress gradient it also wants to zero itself. And then when it does, you will have a bent structure. So for the stress gradient to go away, this structure will have to bend out of plane. And that creates problems in some situations. Your device is not staying in plane anymore. And therefore, we have to make sure that we're managing the stress in these structures as well as we can. Sometimes there are device design solutions that you have to take into account. So for example, if you use a fixed beam, well, it cannot really bend out of plane that much. If you have tensile stress instead of compressive stress in your films, well, if you release them, they're not going to buckle, they're not going to bend out of plane, they're still going to be stretched and they remain straight. So these are examples of processing steps that can create stress in your thin films. So let's just move forward. Another issue, and you already have seen it, that you can have a stress inside the film, is that you can actually have an actual load on the beam while it is bending. And an actual load on the beam, as it is bending, it is going to affect its bending behavior as well. The Euler beam theory has to be modified as shown here. You now have this tensile force that is applied. This is axial load, so if this is the beam that I'm considering, I have a force that is bending it down in this plane, but I have applied T, that is either stretching or compressing this beam as well. And you should expect a change in the bending behavior of this device because of that stress. We'll talk about it when we talk about dynamics in the next lecture a little bit more. But for now, you can show that a beam under tensile stress becomes actually stiffer. It behaves as if it is stiffer. On the other hand, if you put a compressive stress on the beam, it behaves as if it is made of a softer material. This is the solution to that equation for a clamp beam. Now, an issue that arises from there is buckling. So you know that if I put too much stress on a beam, compressive stress on the two ends of a beam, it will buckle. It will not stay flat. At some point, what does that mean? Buckling means that it lets go. The spring constant that I had for this, for the tiniest amount of normal forces, will be 0. So it just buckles up and lets go. How much force do I need to make that buckling happen? Well, it depends on the boundary conditions and dimensions of your beam, as you expect. Typically, for micro devices, we do not have enough forces at those dimensions to make things buckle. If you do not have stress, if you do not have a pre-stressed structure, you normally cannot produce enough forces for buckling to happen. But sometimes with material engineering, you can come up with tricks for that to be the case. You can create buckled structures and bent structures through some combination of applying a force and taking advantage of material properties. Now, last thing to discuss here is bending of plates. So a beam is a one-dimensional element. You're only considering the behavior of this one-dimensional element. Yeah, I know we have width and height, but essentially it's a 1D element. Plate is a 2D extension of that same element. So what you expect to have is a similar behavior, but expanded in 2D, 2 dimensions. So for a plate, the deflection equation, this is for a beam. For a plate, you get a similar behavior, but now the derivative is with respect to both x and y. And instead of using a simple Young's modulus and the moment of inertia here, we need to use this flexural rigidity, which is representing EI and is given by this value over here. And instead of a simple distributed load along the length of the beam, now you have a pressure applied at locations x and y. So in general, it's a very similar problem to what you had for the beams, but the solving of it is a bit more complicated, and for most situations, we don't really have a closed form. For a circular plate, it's fairly simple to solve. You just switch the coordinates to the cylindrical coordinates, and everything will be a function of radius because of the symmetric nature of the problem. So it becomes a fairly simple problem to solve. But going away from that, even for a simple square shape, you don't get a nice, clean, closed form expression for this. But there are solutions to the bending problems for plates of different geometries that you can just pick and use. Now, that is the end of discussion for the static response of beams and plates. In our next lecture, we talk about the dynamic response of these devices, where we see how they respond to loads that vary in time, and then, forced or unforced responses. Thank you.